So thanks for your time and would welcome any questions. So the title of the presentation is Embracing a Silicon to Systems Approach. This silicon to systems phrase is really catching on. We're seeing it being used as that footprint to describe the back end. And then let's get into some of the regional versus global supply chain things that we're seeing. So hopefully you've been looking at this image in the bottom right-hand corner as I introduce the talk, and hopefully you're staring at the substrate in the middle. This comes from our presentation from SEMCO last fall at our Advanced Packaging Symposium in Washington, D.C. What you see here is chiplet architecture. You see the combination of CPU, GPU, MPU, neural processing networks for AI, stacked high bandwidth memory, all of these things coming together in a single unit. What you also see are a variety of embedded technologies. These can also be active or passive in nature, whether they're silicon bridges or chip caps, resistors. On the power domain, we're seeing a lot of incorporation of embedded magnetics for all various reasons, and again that part getting down onto the board. What you're not seeing is the scale. We'll talk a little bit about this later. 32, 35 millimeter packages, obviously getting much bigger. 75 millimeter, 85 millimeter, and we are now getting back. I think it's called Back to the Future, I guess the movie is. We're seeing over 100 millimeter, 120 millimeter packages, MCM, what used to be on ceramic days, now on these organic buildup structures. So we'll come back to this image a little bit later. Let's start at the top level, some introduction, some messages, drivers, and a little bit on the CHIPS Act updates with some definitions. So first off, don't need to spend too much time on this one. But we're here to help the industry support our members to build electronics better for over 60 years. This year, 2023, we are now surpassing over 3,200 member-based companies. So a member is a company, not an individual. Obviously well known for standards in education, but what I'm going to be showing you today is a little bit lesser known, I guess, on the advocacy, what we're doing with governments and technology solutions, which I run. A little bit about technology solutions. So a lot of this is new. I joined IPC in 2020. My mission coming in was to build more technology horsepower within inside the organization to help members, along with all the wonderful volunteers that spend a lot of time developing standards education and other messaging to the industry. I won't read all of these things, but obviously looking at identification of needs, my job basically is to make sure we're working on the right things. It takes a lot of time and effort to take a look at the various elements and making sure that this is what the industry needs and wants, and then pouring those that voice of customer into what is wanted kind of at the product level, whether that be standards development, industry research, education training, or events, getting the networks together. What you're seeing here in the bottom is the key initiatives. Again, these are all running in parallel: design, advanced packaging, factory of the future. This is how things are made, e-mobility, automotive electronics, and then our core technologies, which I know is much of the focus within HDP. I would be remiss to talk about sustainability. This is a separate effort led by Dr. Kelly Scanlon here at IPC, realizing what's going on in our planet today. We need to be much more responsible from a sustainability, and we know that starts at the design point. Want to just communicate here that really spending a lot more time on an industry group collaboration. This is not being done in a vacuum. We're trying to spend a lot more time with groups like yours at HDP. Over these past 2 years, spent a tremendous amount of time at SRC, Semiconductor Research Corporation, and NIST, as well as some of the different organizations depending on the field of study. If you haven't seen this report yet or read it, I recommend you do. This is still being downloaded even this week. It's amazing the traction that it's got. It's basically been helping to influence US and European policy, CHIPS Act on both sides of the Atlantic, CHIPS programs, as well as public and private investment. Take a look, the link is there. We spend quite a bit of time doing voice of customer research, understanding what is really being needed and what the gaps are. Wanted to share this one. This was, for those of you that know Todd Youngkin, he's the president and CEO of SRC. This is his quote, which I use literally every day. Advanced packaging is the new king. If you stop and think about what he's saying, and he is the president of semiconductor facing companies and saying that packaging is really the new gate with 3, 5, 2 nanometer nodes well on their way. How do we package that? How do we get this into products? So really, really important concept. Well, again, we'll come back to this in a moment. We've been spending a lot of time trying to get the right people together. Many of you, I was looking on the chat session, I recognize from a lot of different areas. So nice to speak with you again, and too bad we couldn't see each other, but attended also this packaging symposium, which we held last fall, very well attended. It really just highlighted the demand for what is needed. Again, we'll talk a little bit about this 20-25 year supply chain gap that has occurred, and really trying to get to the root of what we can do about it within the U.S. region. Likewise, in the spring of this year, we were off to Brussels and Belgium, again dealing with that region's most important elements. This was the week of the European Union CHIPS Act announcement. So this was very well timed. The speaker you can see in the middle of the slide is actually, she's from the European Parliament itself. So we have strong allies inside governments to make sure that we're getting the industry's voices heard. This is Miss Ava Maydell. If you're following the CHIPS Act policy, just a very strong advocate, making sure that the back end of the system ecosystem is included in this. So same thing. You can see some of the panelists from Bessie, Amcor, AT&S, and Fraunhofer getting into details on what is needed from equipment, materials, and design aspects as well. So just the key message was showing you a few of these examples is that we're really focused on making sure we're interacting with the industry very publicly and balancing what is needed both technically and at government levels. Last thing I'll show is the work we pour into getting this messaging out. You'll notice, Jim, I see you online, so you're jump starting the U.S. semiconductor packaging white paper that was thought up of you at the very beginning of this. Ended up getting a lot of attention as well, both U.S. and Europe again. In the bottom right, you can see this is actually a news article that was published in the summer by the New York Times. Again, the point is that we're getting our advocacy message out that back end of the ecosystem is just as important and complex as multi-billion-dollar substrate facilities. Let's get into some key messages. So if I have to stop here, we can walk away with this slide. I was taught a long time ago that everything follows silicon. If we would continue to remember this, much of what happens after can really be focused on ahead of time. We are at the very beginning. It's already started. This is not something that's coming. This has been argued, maybe already been in motion now for the last 3 to 4 years, primarily in Asian leading countries. But we are in for a decade-plus long technology disruption that are chiplet-based with heterogeneous integrated structures. What we continue to see is primarily within the European Union and the United States is a semiconductor focus. I'll get into more detail here as well. This is great, absolutely important, but it is insufficient. We know we don't carry pieces of silicon in our pocket. We carry cell phones and use computers and kind of final systems in our hands. There's a strong need for silicon to systems. Again, we use this as a coin phrase primarily within government so that there's a lot of non-technical people that are really trying to understand some of these details and why they're so important. So this is what we use as phrasing and methodology. And basically it means to be working beyond these semiconductor technologies, primarily substrates, OSAT IDM assembly, Ultra HDI PCBs, and a new term which is starting to we're definitely promoting it is complex integrated system assembly, and I'll show you what that means as well. Lastly, direct versus indirect impacts. So for the component makers, this is already in front of them. So how are we stitching different node semiconductor chips together, substrate improvements, the packaging assembly, all of that is upon them right now. However, if you're not actually a component maker, synchronize your watch, because as a PCB fabricator accepting these parts or an EMS provider building these parts, there will be significant impacts coming, as they have been for the last 20 years, but it's going to get, I think, even, I'll call it bigger and badder as these parts get bigger and smaller all at the same time. This presentation includes insights from over 2 years of work, and you can see we work very closely with Department of Commerce, Defense, NIST, the NSC actually, SRC, ASIC, and the European Commission and member state parliaments. Okay, so let's get into some detail here. So I don't need to say too much about this. It feels like everything's happening at the same time. I don't know if it's a combination of just us coming out of COVID where it seemed a little slower, but wow, everything is really piling on top of each other. The rate and pace of these disruptive technologies, shortages, geopolitical conflicts and tensions, inflation, the need for resiliency, all of these things are happening at the same time. And what this is leading to is us rethinking a global plus regional supply chain model. Let's talk a little bit about that. So I guess I can use myself as a good example. I entered the industry in 1998. For the last 20 plus years, we have seen a global outsourcing market. I was taught in business school that you are dealing with a horizontal supply chain, dream it, design it, and go get it built wherever you need to make a profit. And what we're seeing is that needs to change somewhat for different reasons. There are new goals that are really becoming more important: resiliency, continuity of supply, this idea of industrial commons, and security. A point on industrial commons. You see a Harvard Business Review article dated 2009. If you haven't read this, I recommend you do. It's absolutely interesting how applicable it is to today. I think it was the Kindle kind of reader screen that was used as a hardware example. We could switch that out today to something else, but all the ideas and comments about bringing in all that skill, whether it's that that PhD chemist all the way into on the floor technologists and line operators. All of this is what builds what's called an industrial commons, and once that is lost, it is very hard to regain. And we know that this is as much about people as it is about the technologies themselves. Now that said, having that kind of in mind, there's some very real challenges, and the number one that we have seen is this domestic demand signal. It is still not answered. We ask very difficult questions to United States DoD primes, for example, or other commercial electronics providers that are international in nature. Are you really going to build or source a particular element or the final system domestically? That becomes a very difficult problem. What I do want to say is that we need to think about these models in a different light. If this is just about can we build it at cost parity or less, this discussion is a very short one. We already know the answer. Building things with Factory of the Future, Industry 4.0 techniques in mind is an absolute must to try to get at some of these OPEX, CAPEX issues, but that's still likely going to be insufficient. There are significant switching costs. If you're building something in Asia right now and it's working great and you want to pull it back to the US, for example, I remember failing suppliers for 2-3 years there's a significant cost to that as well. So this obviously does not go with an easy transition. But as IPC, as a global trade organization, we are very careful to make sure that we are working with the industry at a regional plus global supply chain model. The global supply chain is alive and well, but for reasons, whether it be security or resiliency, continuity of supply, we are seeing that people are interested in paying premiums. We pay premiums every day for a variety of products. Those types of conversations are now starting to emerge. Important industry drivers. Again, I won't spend too much time here other than to say that the IC market is setting yet another all-time high, 480 billion in 2022. The image on the right-hand side, you can see a slow, steady increase since January 21. That's a 4x increase that you're looking at. The electronics we know are ubiquitous. They're just being used everywhere, more and more each day. Want to talk a little bit about EMS and PCB fabricators, that indirect impact I was talking about earlier. So there's two things I want to highlight. One is this idea of complex integrated systems. Most of us on this phone call are highly aware of these as disciplines, but are starting to come together, and I'll share a little bit with that. As well, I mentioned these large body sizes. So 120 millimeter packages, chiplet based, less than 30 microns on a UHDI. This is starting to get really bad, really hard, but is going to be needed for HPC computing. Let's take a look at these numbers one more way. So again, looking a little bit ahead of us here in 2027. So this market is growing, getting up into the $900 billion range. Half of that of the packaging revenues are looking to be more advanced packaging structures as opposed to just wire bonded or some of the conventional structures that have been the horsepower over the last 20 years. So this piece of the pie is growing for these advanced packages. And then of that 122, 15%, which is the next biggest segment behind flip chip, is again emerging 2.5 and 3D structures. So these are very, very large signals of the technology being used within products. Okay, let's move to the couple of CHIPS Act updates. So on the US front here, if you're not familiar with the chips.gov website, this is where I recommend you go. The last couple of weeks here, the DoD named 8 locations to serve as the new microelectronics commons hubs. And then just last week, the selection committee named their leaders for the NSTC. So announcements are coming out literally weekly. I think most of us are familiar with these dollar figures and will not go through them other than to say that to simplify, there's a lot of money out there and, well, a lot, but maybe not a lot, split into 2 areas. So one is the incentives program. So these are for large scale manufacturing operations. The second, the 11 billion, is for future-looking R&D. So the NSTC, the NAPMP, the Manufacturing USA Institutes, all of these fit within the R&D 9906 element. European Union, you're seeing similar numbers, around 43 billion into 2030 timeframe. Again, what we've seen is European and North American needs and gaps are very, very similar. There's obviously some differences. Much of the design horsepower still comes within the United States, but there's a little bit more, for example, substrate and PCB capability in the European region. The one thing that I want to highlight for this group is that in regards to the U.S. and European CHIPS Act, there's this notion of pilot lines and, trying to get from onesie, twosie, going through this valley of death into commercial volume manufacturing. We know, all of us, how hard that is. Therefore, the installation of pilot lines to be able to dream, develop, and kind of, build up that S curve to get into something of production. This concept is very much fundamental within the European CHIPS Act. with one major difference. Europe has Fraunhofer, IMEC, and CEA Leti, which are already well-established institutes being able to drive this notion. Flip side, when we look at the United States, we are still trying to figure out who will do that, what type of capabilities, and how to coordinate that. So in this regard, look for some really nice advancements with the EU Chips Act when partnering with these institutions. I get this question almost every day. What is advanced packaging? You can see the funny image on the left-hand side. I recognize some of these products for when I was younger. Imagine all of that now in your phone. We often forget that that is actually what is in our phone today. Advanced packaging is the process by which an advanced package is made, and an advanced package is a certain category of electronic component. It's as simple as that. We get mired in a lot of technical words and kind of, you know, the word semiconductor people get interested and excited about, but an advanced package is one grade, one technical advanced package type. It serves really important functions, as we know, compute, memory, storage. And as we start to see this miniaturization get into even yet another layer of complexity, it's really because we want the consumer demands miniaturization, multifunctionality, speed, performance, and bandwidth. And if we do this virtual teardown of this iPhone, you can see how things are getting smaller and smaller and smaller. One thing I want to comment on is that what I find really interesting about this chiplet and heterogeneous integration problem is that it's actually generating extremely large packages, which I just mentioned, 120 millimeter packages for HPC, and it's also producing extremely small packages on the order of 1 millimeter and smaller, driving miniaturization. So we have the biggest packages you can dream up, and we also have the smallest packages you can dream up. Really, really interesting when you think about the differences in challenges there. What are complex integrated systems? I'm using a slide here from, many of you would know Dan Gamoda, Vice President at Jabil Circuit. We have been involved in this stuff in silos for many, many years, so I'm not claiming that any of this is new, but what is new is the integration of all this all into a single product. Optics, photonics, electromechanical design, these advanced substrates, and new materials needed to balance electrical, thermal, and optical mechanical properties. One good example of this is our ADAS systems in vehicles. All of this stuff is happening inside single packages in very, very small form factors. When we start bringing in the notion of not just the actual advanced package complexity, but now making a system smaller with a lot more alignment capabilities, etc., the complexity of building these is going up, excuse me, from a system level as well, not just the component or the chip level. Okay, let's move on to this notion of an ecosystem beyond semiconductors. We'll get into a few trends. Again, I'm assuming many of you are well aware of this. So people love to talk about silicon. This is one of the things I've learned over my 3 years. Here's a quote from former Intel boss Craig Barrett, who also was just named as part of the NSTC leadership. Microprocessors probably the most complicated devices ever made by man, and this continues to get more and more complex and expensive. One single chip fab on the order of $20 billion, $5 to $8 billion every 5 years to maintain it and keep it at its current node level. What they're not talking about is this, how this gets packaged, and this is obviously is where groups like HDP and IPC and all of us here are, this is where we live and breathe every single day. How we're bringing in compute, high bandwidth memory together, how are we're bringing things together in a reliable, quality, yet performance-based way. One of the ways that we try to describe this to governments is kind of that three-legged stool approach. So in the bottom left, you're looking at that finished component, that advanced package. I know this is an older image, but we're just trying to stay away from any intellectual property. It's made of 3 components. It's made of silicon, made of a substrate, and then it is assembled and packaged. As we've said, most of the spotlight continues to be put on silicon. Again, extremely important and exciting that that is happening, but on its own is insufficient. I'm going to show you a slide here in a moment that regardless of the configuration of the top of the stack, it still ends up on a substrate at some point, at least for now. And that needs to be put together reliably and tested and kind of ending up with the component. So this is how obviously we make a component. Now, what's interesting is that if we expand this into this, the systems level, and this is where I spent all of my career on the system side, and you can see on the left, we're going to go left to right here. On the left-hand side, you can see that same BGA component, whether it's a computer or logic device. While it's important, while it costs a lot of money to make, it is still one part of a bag of parts. Part number counts that I was used to dealing with were 8,000, 10,000 parts. So just, a critical important component, but still just one. You need to fix those to printed circuit boards, build those up, bring in hardware, electronics, and mechanicals together to end up with the final system. This is what we are working on within IPC to further improve coverage on the left-hand side in terms of componentry and on the back end of final system assembly. So this is the notion of the ecosystem beyond semiconductors, which definitely needs more attention. Now, the interesting point here is that the gap between wafer fab and system level type of needs is narrowing. Not too long ago, I would estimate inside of 10 years. I can think of 6, 7, maybe 8 years ago, wafer-based processes and panel-based processes were separated, not just in terms of design rules, technologies, materials, but also in skill, know-how, and personnel. You could drive a bus through these two populations. That's not true anymore. This is literally the round hole in the square peg analogy that is funny to use, but is seeming to be true here. If we are going to advance the state of the art with these new, whether it be ultra small or very large type of devices, we need a greater coordination across IC design fabrication, substrates packaging, and the final system assembly. Again, this notion of a complex integrated system, they all have very important roles that touch each other. I mentioned earlier direct versus indirect. These direct impacts are being felt right now. This is why we're seeing so much funding coming out right now for the fabs. And we're spending a lot of time making sure that money goes to substrate and package assembly and test facilities as well, because again, you can't build this stuff without those. Indirect impacts, Ultra HDI, I'll give one good example. So I cannot name names, but we're in a situation where we can be using state-of-the-art chip technology in the United States, but we are dumbing down our designs because we cannot use that technology on a printed circuit board that is domestically fabricated in the order of 0.3, 0.4 millimeter pitch on the BGA. That's very alarming to security and government because we're not able to use the state-of-the-art that we want to. Again, this is a great example where just because you can deliver state-of-the-art chips doesn't mean you can use them in a system. Here's Moore's Law since the early 70s. You can see the red line starting to curtail off. Advanced packaging is the new king I mentioned. The concept of using chiplet architectures and heterogeneous integration is, I'll call it cheating. It's a very effective way to get back on to that line that we've dropped off with, particularly as we've hit 10 nanometers. You can see on the node side that we've started to slow down. So this is really the driving force why we are getting into these architectures. Some people call this Moore's Law 2.0, whatever you want to call it. It is here to stay. You can see some numbers. IBM put out 2 nanometer technology, I think it was last year now already, and looking to be in production by 2025, and getting into basically gate all array transistors and getting into much smaller than even 1 nanometer structures. Chiplets, I think one of the biggest takeaways here is that, stitching components together, or excuse me, stitching silicon together is really meant to be able to use state-of-the-art and common node sizes. So this isn't just about going state-of-the-art, 2, 3, 4, 5 nanometer nodes, but it's also coupling it with a 90 nanometer node to produce that other element in the device. So this is a very, from an electrical and chip design perspective, this is very, very challenging. But again, everything follows silicon and will have impacts onto that interposer and final package. The days of monolithic silicon are slowing. I don't think they'll come to an end, but these multi-chip chiplet architectures, again, are here to stay. So let's keep drilling in to the details here. So we were asked in May this year to provide recommendations on behalf of the industry to the Industrial Advisory Committee, which is part of the National Defense Authorization Act, to the CHIPS Act, and wanted to share with you some of these results. Unfortunately, many years ago, the United States decided not to invest in IC package substrate production. And 20 years later, we find ourselves in a very difficult position. As we know, advanced substrates require state-of-the-art know-how, equipment, materials, and processes, where the rest of Asia, Japan, South Korea, Taiwan are very much ahead of the curve, and to some degree, Europe is as well. So the supply chain that I've seen over these past 20 years is that horizontal global supply chain, which is fine to use, but if there are disruptions in the world, whether they be geopolitical or whatever, this is what's causing people to rethink some of that strategy. So I'll give you one example. So there's four of the major foundries that are going in the Southwest United States right now. Once those chips are fabricated, if we do not have substrate or OSAT capability ready to supply them, then what's the very first thing that's going to happen once they're produced is they get on an airplane and they go to Asia to finish the process. So in essence, we're not really shortening the supply chain, we're actually lengthening it. Few images here, lots of different packaging options. This is just the tip of the iceberg. Silicon interposers, fan out on substrate, embedded bridges, RDL, 3D stacking. What's interesting about all of these techniques, which are developing simultaneously or evolving, excuse me, is that at the end of the day, maybe not forever, but for now, all still end up on a substrate. It's very, very important to realize that. A couple of roadmaps to share with you. This is one that came out of the ASIC coalition that is still in action. You can see here again, this is just a subset of some of the variables, but what I want to show you is kind of these columns where we've got state of the practice going out to state of the art on the right. So 912, very common for substrates within the next 5 years, want to get to 5.5 and then getting into 2.2. Now, from a substrate perspective, when we think about can we do that today, it's extremely challenging. In terms of the equipment set, environmental handling, clean rooms, and quality reliability, as well as metrology, making sure that we're putting out good materials in advance. Here's another, again, I won't go into the detail, but here's some more information from Northrop Grumman, Helen Phillips. What I want to really show here is that this is not just a one size fits all. There are many, many different things going on. High density interconnect at the PCB level, organic buildup layers, glass substrates, and even silicon-based, wafer-based processes. Again, I mentioned that these worlds are colliding. This is a good example of that happening. And trying to service this all into their product needs. This is an example of what the Department of Defense is using. I'll pause for a second. Most of the time that I've seen over the last 20 years, not a rule of thumb, but Aerospace and defense, electronics generally were followers, not leaders in electronic packaging for very good reason. High quality, high reliability, tried, tested, and true. One of the biggest observations that I've made, especially this last 2 years, is that they are now asking for state-of-the-art electronics. This is different than what was being asked for. You can see the challenges that come along with that. Let's take a look at some commercial, I guess these are in essence roadmaps. So this again comes from Richard Bay from Semco, I think they're number 3 in the market leader list for substrate capability. I really like this. For those that were in Washington, you've seen this before. It combines I/O speed, fab node, line space, bump count, and layer count all together. You can see our monolithic piece of silicon on a 50mm package in the bottom left, and you can see that migration as we go into the upper right. Same information, but a different view. Conventional versus leading edge. What's interesting, and I shared this at Apex this year as well, is that from a market leader's perspective, the image on the left, they consider conventional. I would argue that many suppliers in Europe and North America would aspire to some of this. This is chiplet architecture right now. You can see the CPU, NPU, stacked memory all in one package. But what you do see is you see I'll call it a naked substrate, right? So it's just basically using it as a routing function down to the board. What you can see on the right-hand side is, again, that integration. This is the image I showed on my title slide, the integration of embedded actives and passives for many reasons, right? Electrical signal integrity, thermal, power dissipation, and in terms of power electronics, a lot of the embedded magnetics, again, trying to get down those parasitics. So there's a lot of reasons why this is the driving force. What's really shocking when I first saw this was that this is not future looking. This is in qualification. So this really shows what the market leaders are already doing and working on today. From a global supply chain perspective, I mentioned, unfortunately, after 20 years of outsourcing, the US now designs products it cannot build. And this is really the essence of the CHIPS Acts. Much of this same messaging holds true for Europe. You can see some of the stats here. 85% of the designs that still come out of commercial and defense electronics are still born, obviously for intellectual property reasons within the United States, but the majority of that is built elsewhere. We know this very well, but it brings in these concepts that manufacturing matters and that we need to rebalance or rethink how we deal with our regional and global supply chain models, which I discussed. Here's an image of some ecosystems. So let's go right side, left side. So on the right, the mighty island of Taiwan. This is why there's so much consternation with some of the geopolitical issues within the strait between PRC and Taiwan. You can see here that all of the major elements, these are top 20 producers in each segment are pinned here. So this is not just anybody who's building this. These are all market leaders, all contained within close proximity. Again, with availability to truck transit, they can basically design something in one facility, run it overnight by truck, and have it there the next day. This is what really is, I think, the secret sauce to driving speed and mobility of development of next generation products. And same thing you can see in Japan, South Korea, and expansion of capabilities in China. On the left, in the United States, what's interesting is that we actually have a lot more semiconductor fabs and foundries than people really realize. It's really the lack of substrate and OSAT facility that is needed. So the problem statement that we took to the IAC is that there's still far too much emphasis placed on semiconductors, important but insufficient. We virtually have no substrate capability. This is not a bring it back story. This is we've never had it in the first place. And that if we're going to be able to build this type of component, that we need to increase that capability. And I mentioned the lengthening the supply chain, not shortening it. So the grand challenge, and very simply, is an ecosystem focus for critical systems. We continue to ask what those systems are. They are likely going to be defense systems, but they could be banking systems. Imagine if the stock exchanges went down. It could be medical systems like COVID. It could be electric vehicles or transportation. So whatever that list is, what is it that we're actually needing to build, and then wrapping the solution around that. And I won't read all of this, but it's basically just talking about going from substrates and packaging into the final product assembly itself. So I want to spend a minute on this slide. So this is what I think caught the attention of the IAC. So even at this late point in time, remember, we are 2 years into the CHIPS Act, and this is what we have heard from our members. So in order to clearly identify what the objective of the CHIPS Act, we need to understand what that objective is. And so I'm going to propose 3 options. So if the objective of the CHIPS Act is to protect and advance US semiconductor dominance, which we've arguably had since the 50s and 60s, then invest in semiconductor fabrication, whether it be microprocessor or power electronics, and then continue working within that global supply chain with allied nations for ITAR waivers, globally sourced substrates and package assembly, etc. This is what I've known my whole career. However, if the option or the objective of the CHIPS Act is to domestically manufacture a certain category of components, CPUs, GPUs, MPUs, memory, then you need to invest in semiconductor substrate and component assembly and test. It's that component at the end of the day. That is a for sale part number. Or if the objective is to domestically build mission critical systems, as I just mentioned, defense, HPC, medical, then that equation just keeps getting longer. And I'm doing this very deliberately. Then it's semiconductors, substrates, assembly, all the way to final system assembly. And what's really interesting is that even after 2 years of doing this, the objectives are still fairly unclear. We're getting a lot of questions from members on, are we actually just trying to build silicon? Are we trying to build a certain category of components? Or are we actually trying to build certain categories of systems? This is what really grabbed the attention of the IAC. Let's switch gears for a second into substrates. So at IPC, with the background in printed circuit board assembly, and PCB, Institute for Printed Circuits, we spend a lot of time on substrates. We recommend that near term, somewhere in the order of $700 to $900 million is what it will take to bolster substrate investment. If we're looking longer term into glass substrates or silicon carbide or exotic materials, kind of that leapfrog technology that a lot of people talk about, we're well into $1 billion just for substrates. The image in the bottom left here, as you can see, again, this comes from our report, showing the variety and span of technology capabilities by country, where US is lacking and Europe is as well. I'm not going to spend too much time here because I want to get to questions and some dialogue, but we go into detail here in terms of what it would take to stand up a substrate facility here. The point that we want to make is that we're not talking about building high volume substrate capability in this country. What we're talking about is building minimum viable capability. Arguably, it's playing catch up, plugging a 20-year gap. It's to enable today's 9 and 12 line mill spacings on ABF organic buildup substrates. It's really playing catch up, but it's basically the fastest path is through joint venture with market leaders, as I've mentioned. This is how we can get around this resiliency problem that we have. On the longer term side, looking at 5 to 10 years, if we're talking about this real leapfrog technology, getting into real miniaturization or embedded technologies, we're talking about a lot longer time. Academics obviously plays a much larger role in here, where we can talk about university research facilities, bridging into PCB fabs, substrate fabs, startups, all of this will take quite a bit of time. What I'm trying to say in these last few slides is that we have a fairly large hole to get out of. It's taken us 20 years to get to this point. What makes us think we're going to get out of it in 5? I won't go into this slide too much, but again, what I want to focus on again is this ecosystem approach. If we're going to do similar types of investment and activity in advanced packaging, assembly, and test in ultra HDI printed circuit boards or ultra printed circuit board assembly or complex integrated systems, there's a lot of work that needs to be done in these areas. We've put in some dollar figures and some timing. What I want to focus on is this, $3.5 billion type of investment, which is not necessarily being talked about at the high levels. This is how we're trying to put investment against the rest of the ecosystem that is needed. So our recommendation summary to the IAC was that even at this late stage, we need to clarify objectives. Are we really looking to continue silicon dominance or semiconductor dominance? Are we looking to build actual component sets, or are we actually looking to build real systems? I don't get an answer when I ask that question. We're really talking about building a robust, resilient supply chain over the longer term, and you can see its elements there. And specifically, again, for substrates, because this is where, and I'll go into this in a moment, where IPC is spending a lot of time now, where we can hopefully work more closely with you at HDP, is spending time on that bridge between HDI, UHDI, and substrates. These design points, materials, and quality reliability requirements are really getting close together. I'm going to skip that slide. Here's kind of the exciting news of all this. So then, following those meetings, the IAC on June 6th produced this. This is from the IAC, and you can see, and I know I realize it's a lot of words. Please review this following the presentation. But you can see that substrates and assembly made the list, and it was not on the list beforehand. I believe this is also in rank order. So I just wanted to give you an update there, and the next IAC meeting actually is next week. So we're pushing very hard to make sure that back-end substrates and assembly and tests, as well as system level assembly type of topics are being included. So the last part of my presentation is more specific in terms of what IPC is doing. I work full-time on this myself with a growing staff here at IPC. So you will see tomorrow an announcement by the SRC that a brand new, it's called MAP-T, Microelectronics and Advanced Packaging Technology Roadmap, will be released. You can go to the srcmapt.org website. We played just one part of this roadmap. For those that are familiar with the HIR roadmap, this will be on par with that, and in some cases an improvement to that, just with new technology coming on board. A lot of really good stuff coming out there. We are partnering very closely with SRC on this program and others moving forward. Again, this gets back to what I was saying, everything follows silicon. IPC is pushing much closer to the silicon side of development. The other news that I want to share with you is from USPAE, so U.S. Partnership for Shared Electronics. This is a subsidiary of IPC, primarily for U.S. Department of Defense prime contractors. So on October 2nd, this was announced that the first known effort of its kind in the U.S., a public-private venture for ultra high density interconnect printed circuit boards and integrated circuit substrates, is being moved forward. What does that mean? The first phase of the Sprint project is to define and develop a blueprint of how such a facility might work. Obviously, this is very difficult. I do not want to get in the way of PCB fabricators who do this for a living, but instead it's actually meant to enable some technologies in overcoming some of the capital expenditure hurdles for equipment and trying to figure a way through that. Realistically, what it means is enabling the Department of Defense to utilize much higher density designs in their platforms. And this is basically just starting. So if you're interested in this work, please contact me and we can get you in touch with Nathan Edwards at USPAE. Now, this is one new idea, and I spoke with Larry and Mike and the leadership at HDP before presenting this. So the first disclaimer I want to give is that this is concept only for any companies that are listed here. These are examples. If you do not see our name on this list, there is no emission intended. It's really still just concept. The idea here is that with the horsepower that HDP has, I like to cite the lead-free solder work that has been done over the last 20 years. Imagine if we could replicate something to that effect on advanced substrates, where at the end of the day, new materials can be inserted into this process, into design test vehicles, fabricated, tested with do's and don'ts, and performance coming out of this. So I do know that there are some other groups doing this, but the idea would be that HDP and IPC, along with members, could be working together to develop new US-based workflows for MSAP and SAP testing, develop new test methods and standards, and then really begin the creation of a substrates reliability database. I guess the kind of the near-term item on this would be, if there is interest, how can we work together to develop and submit a budgetary plan for CHIPS proposal coming shortly. Final slides. My main message to you in all of this is that IPC is committed to helping build the advanced packaging ecosystem. This has been elevated to our highest levels within the organization. I work for John Mitchell within the executive team. This is amongst our top initiatives, which is being funded over the next multiple years, focused on substrates, UHDI, and advanced packaging and test. This is not a US versus other geo challenge. This is IPC working across multiple regions, North America, Europe, and Asia, depending on where they're finding those challenges, delivering thought leadership, and expanding our collaboration. I won't read through these next steps. I've touched on most of these, NUCO, the accelerator program I showed you, the materials development workshop I mentioned in concept, road mapping, Mike Carano, we're working with you and others to start to put some more detail in here. What I really like about some of the information shared already within the meeting here today is, the new things that are not in an IPC standard or need to be, we need to strengthen that channel. So whether we can develop a new standard or upgrade standards, this is really, really important moving forward. We have a few events already coming in 2024. So we have Apex, a special session. Some of you attended that last year. And then we have one in each geography. So we're going to be holding an advanced packaging meeting in Washington, D.C. in May next year, one in Brussels, and one in Tokyo, Japan. You can see a list of new standards. It's a small list right now, but we are very interested in developing new pins and building new committees. One example would be a requirement for organic substrates, 6921 and 9712, which are new AOI process controls for IC chip substrates. Last but not least, if you're interested in any of this or you have some bandwidth to work with me on this, we have a kind of an establishing advanced packaging leadership council, which have your insights heard and worked on there. I realize that was a ton of information, and I talked a lot. Thanks for your time, and I'll be happy to take any of your questions. Thank you.